So now we're going to look at Lewis structures of all sorts of different compounds. All right, we have what we left off with, which was the HF molecule, where we talked about hydrogen sharing its electron in, fluorine sharing one of its electrons in. Those two electrons are shared by both. That forms a covalent bond and makes both elements feel like they are like a noble gas. All right. I've already showed you on the screen last time using the dots and the lines to represent this molecule. And we've got our HF, and kind of zoom in on this a little bit here. We've got our HF molecule, and we see that this is depicting what the picture is showing on the right. The electrons that are involved in the bond are here. It's a bonding pair, it's a shared pair, and then we've got also other electrons that aren't. But when we see a good Lewis structure, we can know that the octet rule is being satisfied. Hydrogen only wants 2, but everybody else is looking to get 8 to be like the nearest noble gas. And we said that you could have the straight line instead of the dot line for that molecule. So that's kind of where we left off last time with the Lewis structure. Now, any element in the group which is 7A, okay, is going to have 7 valence electrons. And if they have 7, and we know that they want 8, 8 is our big magic number here, always to go from 7 to 8, you would need to form 1 bond, okay? Always you're going to form 1 bond. So this is, when we look up an element on the periodic table and see what group it's in, we're going to know how many bonds it has, because it's trying to get as many sharing as it needs to be to get up to the number 1. So let's look at oxygen with hydrogen instead. How many electrons does oxygen have? Okay, so find your periodic table and tell me how many valence electrons, or you can't tell me, but work through and figure out how many valence electrons oxygen has. Well, it has 6 because it is in the 6A family. Okay, so it has 6 valence electrons. The next question is, how many does it want to have? Well, that's not a no-brainer because they all want to have, except for hydrogen, 8 electrons. So if it has 6, but it wants 8, then it's got to do more sharing to get from 6 to 8. So here we see on the periodic table, just to make sure everybody's on board, our oxygen has 6 valence electrons. It wants to have 8. So how do we get there? Here is an example of water, okay? Oxygen had 6, so I'm going to circle the ones it had. It had those 2, it had one of these, one of these. So we have the 6 electrons that it had. But it's allowing one of them to be shared with hydrogen. So one of these electrons there, one of these electrons here are being shared with the hydrogen. And I'll put a square around the ones that hydrogen's bringing in. Okay, so hydrogen has those electrons and is allowing them to be shared. And by doing all of the sharing, now the oxygen says, hallelujah, I have 8 valence electrons. I am happy. I'm like my nearest noble gas, which just happens to be neon. Hydrogen is saying, well, I'm happy too because I have my 2 electrons, because these electrons inside here, both the hydrogen and the oxygen are taking claim to. So that is how we look at this and see that this is a good state of using all of those electrons and making all 3 atoms happy. But we will always, when you are in that 6A family, they will form 2 bonds. When we look at a periodic table, and I'm going to pull the periodic table back up, if you're in the 6A family, no, in order to get happy, you got to form 2 bonds, because 6 plus 2 equals 8. We saw already with fluorine and anything in this family, they're going to form 1 bond, because 7 plus 1 equals 8. And we can continue on. Here's another example, oxygen. The molecule O2, that's the way oxygen likes to exist, as the element oxygen. So let's look inside here and what's going on with the 2 lines. The 2 lines mean we are sharing not 2 but 4 electrons. This is what we call a double bond, because it is 2 sets of 2 being shared between these atoms. By doing that, So what's happening really here is this oxygen has its 1, 2, 3, 4, plus 1 here, 5, 6. It's keeping 4 of them but sharing 2 of them. This guy over here has its 1, 2, 3, 4, and bringing those in to share, 5, 6, so all of them are accounted for. But if we look at the oxygen on the left, he claims his 4 that's attached to him plus the 4 more that are shared, and he says, I'm happy, I have 8 electrons. The oxygen on the right has the 4 that he's not sharing plus the ones that have been brought in to share, and he says, I have 8 electrons. So here we have it forming 2 bonds, but those 2 bonds are actually between 2 atoms, and that's a double bond. All right. How about the group 5? Well, if you're in the group 5, and let's see if I've got a periodic table. Well, no, can't back up to that too easily. The group 5 has 5 valence electrons, okay, and that's what it's saying right there. It has 5 valence electrons, but he wants to have 8 valence electrons. So how much sharing do we have to have? You better form 3 bonds in order to do that. So let's look at an example of this. Here's ammonia. Ammonia has the formula NH3. Why would it do that? Well, nitrogen, if you find it on the periodic table, only had 5 valence electrons. I'm going to remind you that this is 2 electrons, this is 2 electrons, this is 2 electrons. Okay? So the nitrogen had 1, 2, it had 3, it had 4, it had 5. Those are the 5 electrons it had. But he needs 8, so he's willing to share 1 in with the hydrogen, and the hydrogen's putting theirs in there, so that now this nitrogen says, I have 8 valence electrons. He takes full credit for the ones that are even being shared. And the hydrogens aren't unhappy either because, of course, they have their 2. So anytime you're in the group 5 family, it is going to form 3 bonds. It doesn't have to be with 3 different elements. It could be with the same element. This is N2. The element nitrogen is a diatomic molecule, and if we circle the shared ones plus the ones that aren't being shared, how many electrons are there? Can you see that it's 8? And if we do the same thing for this nitrogen, all the shared 1 plus 2 more, that's 8. So both are happy. Let's go to one more family. Oops, no, we're not. Since atoms of the, what are those? Those are the noble gases. I can't spell. Noble gases. Exception of helium, they all have 8. Helium only has 2, so they don't form bonds. And that's why they're called noble gases. They're called noble gases because they don't like hanging out with other guys. They are stand apart. They're by themselves. Now, we can force a little bit of reaction on some of the bigger ones, but some of the lighter ones, we can't even force them to hang out with another element. Okay, so we need to know exactly when covalent bonds form, so that when we look at a compound, we'll know whether or not it's got covalent bonds in it or the other type that we haven't mentioned yet. So when do covalent bonds occur? You're going to know that they're going to happen when you see a nonmetal connected to a nonmetal. So we know where the nonmetals are on our periodic table. If we have a nonmetal connected to a nonmetal, they are going to do it by sharing, because both nonmetals are a little bit away from having 8. They just need a couple more. Neither one want to give electrons to the other guy and say, you can have my electron, sure, no problem. They're both wanting more, and the only way 2 things can come together that want a couple more is to do some sharing. Okay? Now, here's a language that we use. If we look through at a compound, and it's all nonmetal, hooked to nonmetal throughout the whole thing, and nothing but covalent bonds inside of that compound, then we have our first subcategory of compound. Remember, we had compounds as the opposite of elements. Remember, we had subdivided these out into metals, metalloids, and nonmetals. Now we have our first subcategory of compound, and that is covalent compounds. Okay, so we've got it subdivided. It's not the only type. There'll be other types that we'll see here in a little bit. Actually, one other type. Boop. Okay, but anything that is only made up of the sharing idea that we've been talking through in this lesson are called covalent compounds. And that is going to be a very important distinction. Why do we categorize? Why do we put things into categories? Because if we know where it fits, we can know something about that substance. We're going to be able to know properties of these substances. What we know about covalent compounds, and I'm going to tell you this already, is that they tend to have low melting points. By low, what do I mean? Okay, water, where does it melt? It melts at 100 degrees, no, that's 0. It's 0 degrees. So below 0, it's a solid. This is in Celsius. At 0 and above, it starts melting. That's a low melting point. But generally speaking, even things that are 100 degrees Celsius, if it melts in that range, we're talking low melting points. Things that fit in the other category, we're talking in the hundreds, thousands of degrees. So we subdivide things up and we break them into these categories because we can know something about them. And as soon as we know that it fits into this category, we're going to know something about it. This is a generality that we feel pretty comfortable with. It's going to have a low melting point. So this concludes our lesson on Lewis structures.